Let's uncover the science behind why paper straws cause soda to foam up. Recently, many people online have asked me why inserting a paper straw into cola makes it foam.
Some say it's because paper straws absorb water, and when water and carbon dioxide mix, they form carbonic acid. As the paper straw absorbs water, the carbon dioxide concentration increases, causing foam to spray out. This paper straw seems pretty stiff if it absorbs
water. Wouldn't that for paper and tissues, which absorb even more, create more foam? Let's test it out. We'll prepare 4 cups and add cola.
The first cup has a plastic straw, and nothing happens because it doesn't absorb water. The second cup has a paper straw, and sure enough, it foams, indicating that the paper straw absorbing water does produce carbon dioxide. The third cup has a more absorbent S paper, and it creates even more foam. Finally, let's see what happens with the most absorbent tissue. Reason is indeed water. As expected, this is called a 3D holographic fan. First, check out the video. When the human eye sees an object, even if it discounts the principle of persistence of vision.
Visual impression doesn't vanish right away. The visual impression of the object lingers for about 0.1 to 0.4 seconds. This is known as persistence of vision. The holographic fan has many densely packed LED lights on its blades, forming a light strip. Imagine that within 0.1 seconds, the fan blade moves from the 12 o'clock position to the 6 o'clock position. As it passes through each position, the LED lights emit different lights at different positions. Due to the persistence of vision, the human eye retains the visual impression of these LED lights within this 0.1 second period. This is equivalent to having countless LED light sources simultaneously displaying in the entire fan-shaped area. With a certain combination, it can display an image.
Additionally, other parts of the fan blades don't emit light.
Some netizens tagged me in this video. It's really cool how the water droplets seem to flow backward. What's the principle behind it? Actually, the droplets are still falling from top to bottom. So, what's going on here? Imagine transparent droplets steadily falling from above.
If the ambient light isn't too bright, the droplets aren't very visible. At this point, I shine a bright light, and you can see the positions of 5 droplets. Suppose the interval between the falling droplets is 0.3 seconds. When 0.3 seconds pass, the next set of droplets moves to the position of the previous set. I shine the light again, and you see 5 droplets in the same position. Repeating this every 0.3 seconds, it seems like the 5 droplets are still in the previous positions, almost like they're suspended in midair. Now, if we change the second flash to 0.2 seconds, the next set of droplets hasn't reached the previous set's position and is slightly higher. When I shine the light again, it looks like each droplet has moved up a bit, as if they're moving upward. So, this is the principle behind the water droplet reverse flow device. At the bottom of this device, there's a small water pump that continuously draws water up through a tube hidden in the column.
At the top, there's a peristaltic pump that produces stable droplets. Inside, there's a strobe light that controls the position of the droplets.
Didn't I see this online a while back? Hasn't someone already explained it? It definitely won't cool down. Some say that when airflow goes through the small opening of a plastic bottle, the air pressure changes.
The temperature will also change, known as the throttling expansion effect. I checked, and it does mention that when gas expands from high pressure through a porous plug to lower pressure, the temperature changes. This principle is used in some cases. According to this, air can indeed cool down through throttling expansion, but it needs to be high-pressure gas. Natural wind through a small opening doesn't have much pressure difference, so there's basically no change. Some say the principle is blowing versus exhaling. Blowing through a small opening feels cool, while exhaling through a large opening feels warm. Actually, it's not about the size of the opening.
It's mainly because the airflow speed is faster when blowing, due to the famous Bernoulli effect. The hot air blown from the mouth also carries surrounding air out, distributing the heat. The fast airflow speeds up evaporation and heat dissipation, making it feel cool. Let's check out a video. Placing 2 poles of a carbon filament in 2 cups of salt water. It's surprisingly light. Can salt water generate electricity? Yes, it can. Look at this saltwater powered fan in my hand.
Each electron lost becomes an ion entering the solution, while oxygen on the other end gains electrons to become hydroxide ions entering the solution. Electrons travel from one end of the carbon piece through wires to the other end, forming a current that can make the small fan's motor spin. But that's not the case here. The 2 cups of salt water aren't connected, and the circuit isn't closed. So why is the bulb lighting up? Also, This carbon filament bulb needs 20 volts to light up, and the temperature must reach 20 degrees. The voltage from salt water is only a fraction of a volt. So how is it lighting up? I see comments from people seriously talking about aluminum oxide and zinc oxide electrolysis cells, like what they did as kids.
Are they not carefully reading the question? So, if this isn't special effects, then the two cups are connected to a power source at the bottom. Let's uncover whether people online are scientifically rigorous. As I set out to find my enemies, I really felt the chill of nature. When you rub your fingers together, smoke appears. This is mainly because some white phosphorus is pinched between the fingers.
How does white phosphorus come about? There's a special magic paper that, when ignited, produces white phosphorus and phosphorus pentoxide. White phosphorus is a substance that easily ignites, with a flash point of only 40 degrees Celsius. The friction from rubbing your fingers generates heat, raising the temperature above 40 degrees, allowing the white phosphorus to slowly burn and produce white smoke. However, I strongly advise against trying this because white phosphorus is highly toxic. Rubbing it with your fingers can make contact with your skin, and it's very easy to accidentally inhale it, which is extremely dangerous.